last lecture we had talked about the technique of recursion for problem solving, and we saw that essentially using recursion a function can call itself, and we can exploit this capability by defining the solution to a given instance of a problem in terms of a simpler instance of the same problem. And we saw several examples of using recursion for solving simple problems. Today we'll talk about how recursion actually works and what happens really when a function calls itself, and how what is really happening inside the machine when a function is calling itself and how the whole thing works. Let's first recapitulate what happens when a function is called by another function. So recollect, when a function is called, the following things happen. Space is created for the local variables and parameters of the function which is being called. The parameters are initialized with the values of the corresponding arguments, and the return address in the calling function is stored. What we mean by return address is the place in the calling function where control will go back once the called function returns, and this is just the statement or part of the expression following the function call. And when a function returns, the space which had been created for the local variables and parameters of this function, that is destroyed. The control goes back to the stored return address where it was supposed to go back in the calling function, and the return value of the function is used as the value of the call expression. Now with recursion, exactly the same thing happens. When a recursive call is made, there is no difference in terms of the kind of things happening when a normal non-recursive call is made. But the important thing to understand is that in the case of a recursive function, multiple instances of the same function may be simultaneously active. What that means is the following. Consider, for example, the factorial function. When you call factorial n, let's assume we have defined factorial recursively as we saw in the last lecture. So when factorial n is called, before this instance of the call to the factorial function finishes, that is before it returns, a call is made again to the factorial function, this time with the parameter n minus 1, and before that finishes, again a call is made to the factorial function with the parameter n minus 2, and so on. So at the same point in time, it is possible that multiple instances of the factorial function or of the whatever the recursive function is, they are simultaneously active, that is, they are not yet finished. Of course, only one is currently executing, but the others are suspended and waiting for the called function to return. Now each such instance has its own copy of local variables, parameters, and the return address. In other words, if factorial n was called, and that called factorial n minus 1, that called factorial n minus 2, and so on, for each of these instances of the factorial function which are simultaneously active, each will have its own copy of the parameter n. There were no local variables in the definition, and also of the return address where the control is supposed to go back once that instance of the call to the factorial function returns. So all these things, the local variables, the parameters, and the return address for a particular function call instance are stored in what is known as a stack frame for the function, and it will become clear shortly why it is called a stack frame. So essentially at runtime, what is known as a function call stack is maintained by the system. So it's a stack of stack frames. What we mean by a stack is what we normally mean by a stack in English usage. A stack is essentially a pile of things placed one on top of the other, and when you want to remove something from the pile, you remove it from the top of the pile, and when you place something on the pile, you place it on the top of the file. So the function call stack is similar. So let's say the function f called the function g, and f itself was called by the main function. So the function call stack will capture this fact. So each element in the stack is a stack frame. So at the bottom is the stack frame for main, and on top of that is the stack frame for f, and on top of that is the stack frame for g. Now the stack frame for any function will contain space for the local variables of the function, parameters of the function, and the return address from the function where control is supposed to go back once the function returns. Okay, so let's now see in terms of an actual recursive function what is really happening at runtime. So the example I have taken is the printint function from the last lecture, which prints a given integer n. So let's assume that the main function calls printint with the parameter value -123, and let's say the control is just before the call to the printint function in main. So at this point in time, this is what the stack looks like. Only the stack frame for main is on the stack. We are not concerned too much about what it really contains. We'll be more concerned with what the stack frames for the printint functions contain. And this arrow points to the stack frame at the top of the stack. This is called the stack pointer. And as functions get called, their stack frames will get pushed on top of the stack, and so the stack pointer will move upwards. And when functions return, their stack frames will be removed from the stack, and the stack pointer will move downwards. So in the first step, when the call to the printint function is made, what will happen is that a stack frame for the printint function will be created, and that will contain space for the parameter n. There are no local variables of this function, and the value of n in the stack frame will be initialized to the value of the argument being passed to this function, which in this example happens to be -123. In addition, the stack frame will also contain the return address where control is supposed to go back once this invocation of the function printint returns. So now printint is being called from this location in the function main, and once printint returns, execution should continue at the next statement. So I am calling this location in the program as R1. So when main calls printint, the return address stored in the stack frame for printint will be R1, and that indicates where the program should resume execution once the printint function returns. So when the function printint is called, the stack frame for the function printint has been created. As you can see, it has space for the parameter n of the function printint and the return address. The return address is R1, which happens to be this location in the program, and the value of n is -123, which was the argument which was passed to the function, and the control has gone to the first statement in the printint function. So let's now trace the execution of the printint function for this value of n and see exactly how the recursive calls are going to work. So the first statement is if n is less than 0. Now n is -123, which is indeed less than 0. So this condition evaluates to true. So the control goes back to the first statement in the then part of the if statement, which is put char the minus sign. And so when we do this, in the output the minus character will appear. Nothing else changes. So that's all that happens. And then the next statement is n assigned -n. When that executes, of course, the value of this n here just changes to +123. So that's what happens. Now the next statement checks if n is less than 10, which of course in this case is false. So we start executing the body of the else part. Now here is a recursive call to the printint function. Now again, what is going to happen is that a stack frame for this call to printint will be created. That will also have space for n and for the return address, and the value of n for that call to printint will be the value of this expression which is being passed as argument. Now the value of this expression happens to be 123 divided by n, which is 12. So the stack frame which gets created will have space for another instance of the parameter n, which will have the value 12, and that will be the top stack frame. and the return address will be this address R2, because once this call to printint returns, the control is supposed to come back here and execute this putchar statement, which follows the call to the printint function. So that's what happens when this function gets called. And of course, as soon as the function gets called, apart from the stack frame etc. being created, control will again go back to the first statement of the printint function. So this is what happens. This is the new stack frame which has been created. Note that it also has a parameter n here, but this time it has the value 12, which is the argument which was passed from the previous invocation of printint, and the return address is also different. The return address is this location R2, and now we have started to execute another instance of the function printint while this previous instance is still not finished. That is what happens in recursion. So again we start executing this code, but note that the value of n is now the n in the topmost stack frame, and which is 12 at this point in time, and the value of n is no longer 123. So even though in the program it is the same n, but at runtime these are two different n's, because each instance of the function call has its own copy of the local variables and the parameters. So let's see. So again the control will flow the same way, since n is not less than 0, n is 12 in this case. So this statement is kept. N is not less than 10, so we start executing the else part, and again there is a recursive call to printint with the argument n by 10. Now this n now evaluates to 12, because that's the value of n in the topmost stack frame. So whenever a local variable or a parameter is accessed, its value is the value for that variable or parameter in the topmost stack frame, even though below that stack frame there may be other stack frames for the same function which also have the variable n, or which have also the same variable or the parameter. So the value of n here is currently 12, and n by 10 would evaluate therefore to 1. So again the same thing happens when this time printint is called recursively. A new stack frame is created with space for n and the return address. The return address is again R2, because again the printint has been called from this location, and therefore when it returns, the control should come back to this statement R2. And once again the function starts getting executed from the beginning, now for a value of n is equal to 1. So again n is not less than 0, but n is less than 10. So putchar n plus 0. So that means putchar the ASCII code of 0 plus 1, which gives the ASCII code of 1, and so the putchar statement results in the character 1 being printed on the output, and this else part is of course kept, and the control goes to the end of the function. Now this function has finished, or to be more precise, this instance of the function execution has finished, and the function is about to return. Now when the function is going to return, what's going to happen is that this stack frame is going to be destroyed, or it is going to be popped off from the stack. This will again become the topmost stack frame, and the control will go back to the location R2, in other words to this location, which is the statement immediately following the call to printint in the calling function, which also happened with printint in this case. So when this instance of printint returns, that's what happens. The stack frame for the topmost printint is destroyed, and control goes to the return address which was stored in that stack frame. So we are now again executing the second instance of the printint function, which was suspended when it made a recursive call to itself. So now the value of n here in this expression is again 12, because the topmost stack frame is this one, and that has a value of 12 for n. So when this putchar statement executes, n% gives the value 2, that plus the ASCII code of 0 gives the ASCII code of the character 2, and putchar prints that character on the screen. And now this instance of the function is also about to return, and when the return happens, again the same thing happens. This stack frame will be deleted, this stack frame will become the top stack frame, and control will go back to this return address, which again is the address of this putcar statement. So that's what happens. Now we are back in the very first invocation of the printint function. The value of n is now again 123. That gets printed. That is divided by 10 and the remainder comes out to be 3. 3 plus the ASCII code of 0 gives the ASCII code of 3. That gets printed. And this invocation of printit is also now about to return. And this time when the return happens, the control will go back to the location R1, which is the end of the function main. So the main function will return, or if there was some other statements in the main function after printint, then those statements would have started executing, and the stack frame for main would now become the topmost stack frame. So the function has returned. So finally we are back in the main function. All invocations of the printent, including all recursive invocations, have finished, and the output is minus 123 as expected. Okay, let's now take another very interesting problem which can be solved very elegantly using recursion, and which is actually quite difficult to solve without using recursion. This is like a puzzle, and it's called the problem of the towers of Hanoi. So essentially in this problem you have these three towers. Let's call them 1, 2 and 3, and initially within the tower number 1 there are these n disks which are placed on top of the other. Each disk has a hole within it, so it can be put inside the tower, and the disk at the bottom has the largest diameter, and the diameter is decreasing as we go up. So this picture shows 3 disks, but in general there could be any number of disks, so we assume that there are n disks in general. Now the task is to move these n disks from tower 1 to tower 3, and in one move what can be done is that the topmost disk from any tower can be removed, and it can be placed on top of the stack on any other tower. But we have to always follow the constraint that a larger disk can never be placed on a smaller disk. Now this actually appears to be a very difficult problem, and for large values of n it can be actually very difficult to solve. If you try hard, you might be able to obtain a solution for n equal to 3, but you will find that as the value of n becomes larger, the solution becomes harder and harder to obtain, and without thinking about recursion, a general algorithm is not all that easy to obtain. But let's think about this problem using recursion. So the task is to move n disks from some tower S to some tower D, and this third tower is there because so that we can place some disks on this tower during the process as an intermediate stop for these disks. So from the tower S to the tower D we have to move these n disks. Now how can we do that? If you think about it recursively, well, the base case is simple. The base case is when n is equal to 1, and when n is equal to 1, all we have to do is take the disk from the tower S and place it on the tower D. That's not a problem at all. But if n is more than 1, then let's think about this problem recursively. So suppose n is more than 1. Now suppose somehow by magic the top n minus 1 disks can be moved from one tower to another tower somehow, and of course that somehow is not really mysterious. It can be achieved by using recursion. So the first step is to recursively move the top n minus 1 disks from the tower S to the tower T, that is the temporary tower, using the tower D as an intermediary. So whenever we want to move some disk, we have to specify one intermediate tower where disk can be stored on their way to the final destination. So suppose somehow we are able to do that. That is, we are able to move the top n minus 1 disks from the source to the temporary tower using the destination as the temporary. So suppose somebody allows us to do that or shows us how to do this step. Then the next step is to move this bottom disk from the source to the destination. So this is an easy step. This we can always perform. And finally, now again the task is to move these two disks from this intermediate tower to the final destination tower, and for this move we can use now this original source as an intermediate tower because it is now empty. Now again, how do we move these two disks from here to here? It's a simpler instance of the same problem, so we can use recursion. So let's assume that by doing recursion we can do that, but once we do that you can see that the problem is finished and we have obtained a solution. So as you can see, using recursion the solution to this problem is extremely simple to obtain, as a matter of fact. So let's write a program to do this. So I have written this function move which solves the tower of Hanoi problem. It has 4 parameters. N is the number of disks which have to be moved. S is the source tower, which could be 1, 2 or 3, and D is the destination tower, which could again be 1, 2 or 3, and T is the intermediate tower or the temporary tower. So initially, if the disks are in tower 1 and they have to be moved to the tower 3, then we'll call this function as move value of n, whatever the number of disks is, 1, 3, 2. The source is 1, the destination is 3, and the temporary or the intermediate tower is 2. So this is the base case. If n is equal to 1, then we just print the move to move the top disk from source to destination directly. This can be accomplished in a single step. Otherwise, when n is greater than 1, we use recursion. So first move the top n minus 1 disks from the source to the temporary using the destination D as the intermediate. So at the end of this step, the configuration will look something like this. This is the source, this is the destination, and this is the temporary. So the top n minus 1 disks have been moved to the temporary, and then move a disk from source to destination. So this disk goes here, and finally move these n minus 1 disks from the temporary to the final destination. These 3 disks go here. So that's all. So the solution is actually extremely simple once you think about it recursively. I'll leave it as an exercise for you to trace this solution using the technique that we just saw for the printint function, and convince yourself, at least for small values of n like 2 or 3, that it does work correctly by tracing the sequence of the recursive function calls and creating stack frames and putting values of the parameters and so on and so forth. So that's the end of this lecture. In the next lecture, we'll continue our discussion on recursion and talk about some situations where we should not use recursion, and how we should not use recursion inappropriately or inefficiently, because as we'll see, it is easy often to write programs which are extremely inefficient when not written properly using recursion.